Hello, and welcome to Differential Equations. This is lecture 22, Eigenvalues. Last time, we talked about row operations. And in particular, we saw how row operations allow us to solve systems of equations. Invert matrices. And compute determinants. This time, we're going to study the eigenvalues of a matrix. Right? Eigenvalues, which you can think of as the characteristic values or the proper values, so eigen is a German word, and it means proper, as in something that it's owned by. So these are the values that are owned by the matrix. Okay, so first definition and then some motivation. If A is a square matrix, then a vector V is an eigenvector of A with eigenvalue lambda if two things happen. V needs to be not equal to 0, and A times the vector V has to be equal to lambda times the vector V. Right? So on the vector V, multiplying by A is the same as multiplying by the scalar lambda. In that case, the set of solutions of the equation A minus lambda times I times vector V is equal to 0. Notice that this is just a rewriting of this equation, right? So if you multiply this out, you would get A times the vector V minus lambda times the identity times the vector V. Identity times the vector V is just V. So this would be A times V minus lambda times V is equal to 0. And that's this equation just rewritten. The set of solutions to this equation, right, which if you think back 2 lectures, the set of solutions to that equation is the null space of the matrix A minus lambda times the identity. This is called the lambda eigenspace of A and denoted eig lambda A. Okay, so why would we study things like this? Well, eigenvectors and eigenvalues are extremely important both for theoretical and practical reasons. So for example, and I'll say a little more in a moment, but the Google PageRank algorithm uses eigenvalues and eigenvectors. Principal component analysis is all about eigenvalues and eigenvectors. And the emission spectra of isolated atoms is all about eigenvalues and eigenvectors. So let me say a little more about each of these. start with Google PageRank. So in the before times, before Google, in the early 90s, the first search engines used text-based ranking systems to decide which pages were more relevant to a given search. So what would happen is you would type in your search terms, and the search engine basically just counted the number of times these words appeared on a web page, right? So this had very little to do with how relevant the web page was to your search, to what you were actually looking for, right? So, you might be looking for, say, UIUC, and instead of getting the front page of the homepage of the UIUC University, you would get whatever page had decided to put into its HTML the word UIUC as many times as possible, right? Or, there might have been news stories about UIUC that mentioned it more times than an actual university webpage. And so you wouldn't get the page you were looking for. Instead, Larry Page and Sergey Brin, when they were grad students at Stanford, came up with the idea that the importance of a page could be judged by looking at how many pages link to it. And you decide how important the given page is, and then you use that to weight how much you value links from that page. So by counting how many pages link to or from a given page, they came up with this huge matrix modeling transitions between pages. The vector of page ranks is then an eigenvector of that big matrix with eigenvalue 1. Right? That doesn't uniquely determine the eigenvector, but if you also ask that the entries be non-negative and that they add up to 1, then it does uniquely determine it. And so that is the PageRank algorithm that Google used when it started. Principal component analysis is a statistical technique used a lot in machine learning that reduces the dimensionality of large data tables. What you do is you come up with new variables, or sometimes they're called summary indices or principal components, that are easier to analyze. They're not easier to interpret. In fact, they're usually really hard to interpret, but they're much easier to analyze. So what you do is you compute the variance-covariance matrix of the data you have in terms of your initial variables. And then you find the eigenvalues and eigenvectors of the variance-covariance matrix. The eigenvectors are the principal components of the data, and the eigenvalues tell you how much of the data is being explained by each eigenvector. Well, not really the data, but the variance of the data is being explained by each eigenvector. So for a silly example, suppose that you are studying a group of athletes, and then you measure things like the height, the weight, and the speed. So of course, there's a lot of redundancy or correlation between height and weight. You expect people who are taller to also weigh more on average. So what you might do is take the variance-covariance matrix of the data, and it might turn out that for the data you have, the summary index, so some linear combination, let's just guess maybe 1/2 of the height plus 1/2 of the weight minus the speed, that linear combination itself explains most of the variance, so that when you're looking at how different players, athletes, measure up with the data you've gathered, it's actually better, instead of looking at one of these three variables, to look at this bizarre linear combination, half height plus half weight minus the speed. Right? That would correspond to the eigenvector being 1/2, 1/2 minus 1, and its eigenvalue being the largest eigenvalue of the ones that your variance-covariance matrix has, right? So if that eigenvalue is really large compared to the other eigenvalues, then what you might do, and you would do if you were doing data analysis, is just keep this one principal component and ignore your original data. So in this way, you've gone from being 3 dimensions to just 1 dimension. Finally, emission spectra of isolated atoms. So if you have an isolated atom or an isolated molecule, this gets modeled in quantum mechanics by an operator on a Hilbert space. So you can think of that as being, it's a lot like the differential operators we've been studying earlier in the semester, but you can also think about it as being some sort of like infinite matrix. And this infinite matrix has eigenvalues, and the emission spectra of atoms, so when an electron goes from one orbit to another, and it emits or absorbs some energy, the frequencies that are observed are exactly the differences of eigenvalues of this infinite matrix. So anyway, point is, eigenvalues and eigenvectors are really cool and really important. So that's why we're studying them. Also, they're going to be very useful when we go on to try to solve systems of differential equations. Okay, so let's start with an example. Suppose we're looking at the matrix A, 2 by 2, so -5, -7, 2, 4. And let lambda be just any scalar. Suppose we want to find all solutions of A times V equals lambda times V. Okay. So we can rewrite this equation as AV minus lambda V equals A minus lambda times the identity times V equals the vector 0, right? And now this is a matrix vector system, which we were discussing how to solve last time. So what we do is we form the augmented matrix, right? So here our coefficient matrix would be -5 minus lambda, then 2, then -7, 4 minus lambda, and then we augment it with the right-hand side, which is just a 0 vector. So notice that, of course, when you subtract lambda times the identity, you're just subtracting lambda from the elements on the diagonal. And when we augmented, we added the vector 0. This is just going to come along for the ride, so that from now on, after this example, we won't even bother including it because it's just 0, so you don't need to write it. Okay, so to solve this system, what we want to do, we want to find a reduced row echelon form, but we don't want to divide by -5 minus lambda if we can help it, since it might be 0. Sometimes you have to. In that case, you just do two cases. So you consider the case where it is equal to 0, and you consider the case where it's not equal to 0. But in this case, we're not going to have to, because what we're going to do is our first row operation, we're just going to change the order of the rows. Okay, so now that we have a -7 there, it's perfectly okay to divide by -7. So we're not going to do anything to the second row. We're going to divide the first row by -7. Okay, and now that we have a 1 right here, we can use this to clean up its column. So I'm going to do nothing to the first row. But the second row, what I'm going to do is multiply the first row by 5 plus lambda, and then add it to the second row. So I'll end up with a 0 here, and then here I have 2 minus 1/7 times 4 minus lambda times 5 minus lambda. Okay, and so now there are two possibilities. Right? I look at this term and, well, either it's 0 or it's not 0, right? So 2 minus 1/7 times 4 minus lambda times 5 minus lambda is either 0 or not 0. Okay, so let's consider these in turn. If it is not equal to 0, well, if it's not equal to 0, then I can divide by it. So then my next row operation brings us to this matrix, and then I can use this one to clean up its column. So I end up with this matrix. Now it's in reduced row echelon form. So I translate it back to equations, and the equation is x equal to 0, y is equal to 0, right? So in this case, since the only solution to a minus lambda times the identity v equal to 0 is v equals 0, 0, these values of lambda are not eigenvalues, right? So notice this equation always has the solution, the trivial solution, put v equal to the 0 vector, right? So because that's always there, it's not interesting. It doesn't tell us anything about A to say that the 0 vector solves this equation. So we're interested in those lambdas when we have an interesting solution, when we have a solution other than this 0, 0, right? So, okay, so this brings us to our second possibility, which is that this polynomial does vanish, right? If it is 0, then, well, I can rewrite it. Let's pull out a common factor of 1/7. And so then I would have 14 minus, and then if I do that product, I have 20 minus lambda squared. So altogether, that's 1/7 times lambda squared plus lambda minus 6, or 1/7 times lambda minus 2, lambda plus 3. Okay, and notice, coming back to this matrix, that if this is 0, right? So if I had a 0 here, then this column has a pivot, but this column would not have a pivot. So this column would correspond to a free variable, which means that I have multiple solutions, right? So not just the trivial solution. I have to have other solutions. So these are the eigenvalues. Okay, wonderful. So I have the eigenvalues, but I want more than that. I want the eigenvectors. So I want to know what are the solutions to this equation for these values of lambda, right? And well, what I would need to do is find the reduced row echelon form of a minus lambda times the identity. But fortunately, I almost have it already. In fact, I do. I just have to plug in the values of lambda. So if lambda is equal to 2, then if you put a minus 2 times the identity and augment it with the 0, then you end up with this when you put in lambda equal to 2. Putting lambda equal to 2 in here is going to be very quick because we already know that if you put in lambda equal to 2, you get 0. That's how we found lambda equal to 2. So we're just going to have on the first row 1 minus 1/7 times 4 minus 2, which is 2, and then 0, 0, 0, 0, right? This translates to equations as x minus 2/7 y equal to 0, 0 equal to 0. And then if I write the pivot variables in terms of the free variables, that's x is equal to 2/7 y.
Okay, I found this on the web for if I write the pivot.
So the solutions would be all of the vectors x, y, where x is 2/7 y and y is just y. So I can write that as y times 2/7 1 with y arbitrary. Right? So this is the eigenspace of A corresponding to the eigenvalue 2. the eigenvalues, so the eigenvalue is 2, the eigenvectors would be any vector here as long as y is not 0, right? Any non-zero vector would be an eigenvector. Okay, so that leaves us with, if lambda is equal to 3, then when I do a minus 3 times the identity, sorry, the eigenvalue is minus 3. So a plus 3 times the identity, and I augment with the 0 vector, then putting this in reduced row echelon form, again, is very quick because I computed it already here, right? So I just need to plug in lambda equal to 3. I know that's going to give me a 0 here, and here it's going to give me minus 1/7, 4 minus 3, so that's a 1, so just minus 1/7. So here I'm going to end up with 1, 0, minus 1/7, 0, 0, 0, which if I translate back to equations is x minus 1/7 y equal to 0, 0 equal to 0. And then if I write the pivot variable in terms of the free variable, I get x is equal to 1/7 y. So the solutions would be all of the x and y, where x is equal to 1/7 y, y is just y. So y times 1/7 1 with y arbitrary. Right. So this is the eigenspace corresponding to minus 3 for A. Okay. So great, that's one example where we figured out all of the solutions of AV equals lambda V with lambda a constant. So let's write this out. So how do we find eigenvalues, eigenvectors? Well, we're looking for non-zero vectors V satisfying A minus lambda times the identity V equal to 0. Right? So we have two methods. The first method, start with A minus lambda times the identity and use row operations to determine when a reduced row echelon form has a free variable, right? So remember, that means a column without a pivot. So in this case, right, we had only one pivot here. So this column is a pivot column, corresponds to a pivot variable. This column corresponds to a free variable. Then you use the reduced row echelon form to find the eigenspace. Okay, so that's the method we just used in this example. There is a second method. First, find the eigenvalues. I'll tell you how to do that in a moment. Then for each eigenvalue, use reduced row echelon form to find the eigenspace. So the first method is more efficient, but it is also messier. And what makes it messy is that you have to do computations like the ones we did over here, where you're doing row operations, but you have a lambda that you don't know the value of. And as I said, sometimes that requires breaking into different cases, depending on whether or not something you want to divide by is 0. Okay, but let's say you wanted to do the second method. How do you do the first part? First, find the eigenvalues. Well, you use something called the characteristic polynomial. Of a matrix. So if you have a square matrix A, then its characteristic polynomial is the determinant of A minus lambda times the identity. Right? And then here's a simple theorem. The eigenvalues of A are the roots of its characteristic polynomial. Okay, so here's the proof. Lambda is an eigenvalue of A if and only if a reduced row echelon form of A minus lambda times the identity has a free variable, right, which is equivalent to saying A minus lambda times the identity is not invertible. We know that it's equivalent because of the method we saw last time for computing the inverse of a matrix using row operations. And we also saw that a matrix being not invertible is equivalent to its determinant being equal to 0. Right? So in this way, we see that being an eigenvalue is equivalent to being a 0 of the characteristic polynomial. Okay, so let's do an example where we want to find where we want to use both methods. Find eigenvalues, eigenvectors of this matrix 1, 1, minus 1, 1 using both methods. Okay, so method 1, right? Method 1 is just to start with A minus lambda times the identity and put it into reduced row echelon form. So A minus lambda times the identity, right, would be the matrix 1 minus lambda, 1 minus 1, 1 minus lambda, right? Last time we augmented this with a column of zeros, but as I mentioned, those zeros just come along for the ride. So from now on, we won't even bother including them. So we're just going to do row operations. I'm going to start by changing the order of the rows. Then I'm going to multiply the first row by lambda minus 1 and add it to the second row. All right, so nothing happens to the first row. Second row becomes here a 0, and then minus 1, and then minus 1 minus lambda squared. Right? So we see that this has a free variable. Right? In order for this matrix to have a free variable, so a column without a pivot, it's necessary and sufficient that this entry vanish. Right? Which happens precisely when lambda is equal to 1 plus minus I. Right? So these are the eigenvalues. Okay, so now I want to find the eigenspaces. So the reduced row echelon form of A minus, let's start with 1 plus I times the identity, right? Well, I don't have to do any more computations. I just have to plug in that value of lambda into this expression. And I don't even have to worry about plugging it into here because I know by the way I found it that it's going to make this entry equal to 0. So here I'm going to have 1, 0, and then since it's 1 plus I, this will be minus I, 0. Right? If I translate this to equations, I get x equals iy, 0 equals 0. Right? Here I've written the pivot variable in terms of the free variable. So the eigenspace for 1 plus I is a set of solutions. So it's all the xy, where x is equal to I times y is just y. So that's y times I1 with y arbitrary. The reduced row echelon form of a minus 1 minus I times the identity. Right? Again, I just need to plug 1 minus I into this expression. So I get this matrix. If I translate this to equations and write the pivot variable in terms of the free variable, I end up with x equals minus iy. And so the eigenspace for 1 minus I of A is all of the xy, where x is equal to minus I, y is just equal to y. So it would be y times minus I times 1 with y arbitrary. Okay, so that's method 1. Method two, you start by computing the eigenvalues using the characteristic polynomial. So the characteristic polynomial is the determinant of a minus lambda times the identity. So here that would be 1 minus lambda, 1, 1, minus 1, 1 minus lambda. You take the determinant, you get 1 minus lambda squared plus 1. And so the eigenvalues are the roots of this, 1 plus minus I. Next, we solve a minus 1 plus I times the identity v equal to 0. So this we solve by writing down this matrix. So minus I, 1, minus I, you augment it, 0, 0. And then you do row operations. So here I would divide the first row by minus I. Then I would subtract the first row from the second. Then I translate back to equations. X equals iy, 0 equals 0. And now x equals iy. So I find the same eigenspace as we did over here. Similarly, I would need to solve for a minus 1 minus I. So here I would have I minus 1, 1 I. Then I divide the first row by I. Right, subtract first row from the second row, translate back to equations, write the pivot variables in terms of the free variables. And I ended up with the same equation I did here. So then I end up with the same eigenspace as I did above. Okay, so the advantage of the second method is that I found the eigenvalues right away. And so then when I went to solve these equations, I never had to worry about lambdas here. The disadvantage is that I had to do the row operations for this eigenvalue, and then I had to do the row operations for this eigenvalue. Whereas with the first method, I did the row operations just once with an arbitrary lambda, and then I only had to plug in what eigenvalue I was looking at. Right? As usual, when you have a method that's more efficient than another with matrices, for 2 by 2 matrices, it doesn't make that big a difference. But as soon as you go to larger matrices, it starts making a bigger difference. Okay, let's do another example. Let's do a 3 by 3 case. Suppose I want to find eigenvalues and eigenvectors of the matrix A. Okay. I'm going to use the first method. So A minus lambda times the identity would be minus lambda 1, 1, 1 minus lambda 1, 1, 1 minus lambda. Okay, I want to put this in reduced row echelon form. So first I'm going to change the order of the rows. So I'm going to put them in this order. You can put them in whatever order you want, but by putting them in a different order, I have a 1 here to start with, so I don't have to divide by anything involving lambda. So now I'm going to use this 1 to clean up its column. So that means that nothing's going to happen to the first row. Then I'm going to get rid of this 1 by subtracting the first row from the second row. So that's 1 plus lambda, and then minus lambda minus 1. And then I'm going to get rid of this minus lambda by multiplying the first row by lambda and then adding it to the third row. So minus lambda squared, 1 minus lambda squared, and 1 plus lambda. Okay, so next I want to make this a 1, right? And unfortunately, I do have to worry about, I have to divide by 1 plus lambda. There's no way I can avoid dividing by something that has a lambda. Even if I switch the order of these rows, I'd have to divide by 1 minus lambda squared instead. So that's okay. We just consider 2 cases. So first, let's consider the case if 1 plus lambda is not equal to 0. Then this matrix, I can do a row operation. If it's not equal to 0, then I can divide by it. So then I just divide the second row by that, and I end up with this. Okay, and now I can use this 1 to clean up its column. So I'm going to multiply the second row by lambda and add it to the first. And then I'm going to multiply the second row by 1 minus lambda squared and subtract it from the last row. So I get here 1 plus lambda minus 1 minus lambda squared. Now, except I don't, because this was a minus 1. This was a minus 1, so that should be a plus. Okay, so in this case, we see that there's a free variable. Right? Notice that this is a pivot, this is a pivot, and this may or may not be a pivot, right? If it's a pivot, then I don't have any free variables. So I want it to be 0 in order to have a free variable. So I have a free variable precisely when this 1 plus lambda plus 1 minus lambda squared is equal to 0, right? Which I can rewrite as minus lambda squared plus lambda plus 2, or minus lambda minus 2 times lambda plus 1 equal to 0. Right? So I'm going to pick up eigenvalues from here. But before we do that, let's keep going with the other case. If 1 plus lambda is equal to 0, then what does this matrix look like in that case? Well, that would mean lambda is equal to minus 1. So the top row becomes 1, 1, 1, and all of the other entries vanish. Right? Let's go ahead and translate this to equations. So that would be x plus y plus z equal to 0, 0 equal to 0, 0 equal to 0. And this first equation, if I write the pivot variable in terms of the free variables, looks like that. So that means that the eigenspace corresponding to minus 1 for A is the set of solutions to this. So it would be all of the vectors x, y, z, where x is equal to minus y minus z, y is just y, z is just c. So it'd be y times minus 1, 1, 0, plus z times minus 1, 0, 1. And here y and z are arbitrary constants. Okay, so now let's look at this. Lambda equal to minus 1, we've already considered that one. So we just need lambda equal to 2. Lambda equal to 2 is also an eigenvalue. A minus 2 times the identity, right? It has its reduced row echelon form. Again, I don't need to do all of my computations from 0. I can just come to here where that showed up. And in this matrix, put in lambda equal to 2, right? Notice that I don't have to bother writing it in here because I know that that's going to be 0. So if I just plug in lambda equal to 2, I end up with this reduced row echelon form. If I translate this back to equations, I get x plus 3z equals 0, y minus z equal to 0, 0 equal to 0. Or if I rewrite the pivot variables in terms of the free variables, that's x equals minus 3z, y is equal to z. So the eigenspace corresponding to 2, right, the set of solutions is all of the x, y, z, where x is equal to minus 3z, y is equal to z, z is equal to z. So that's just z times minus 3, 1, 1 with z arbitrary. Okay, so we found all of the eigenvalues and eigenvectors. Let me point out here, if we had wanted to start by finding the eigenvalues, we would have computed the characteristic polynomial. Right, which is minus lambda cubed plus 2 plus 3 lambda, right? Or minus lambda minus 2 times lambda plus 1 squared. Okay, so here we say that the eigenvalue minus 1 has algebraic multiplicity equal to 2, since it has multiplicity 2 as a root of the characteristic polynomial, right? Lambda plus 1 squared divides the characteristic polynomial. We say that it has geometric multiplicity 2, since the eigenspace, eig minus 1 of A, is two-dimensional. Right? Remember, we found it was equal to this space, right? And so it's two-dimensional because I have two arbitrary constants here, and these vectors are linearly independent, right? So another way of thinking about that is because there are two free variables in the reduced row echelon form of A plus the identity. Okay, so for any eigenvalue, the geometric multiplicity is less than or equal to the algebraic multiplicity. But it can happen that they're not equal. If they are not equal, we say that the eigenvalue lambda is deficient. We also say that the matrix A is deficient if it has an eigenvalue where the multiplicities are not the same. So here's an example where that happens. You have the matrix 1, 1, 0, 1. Characteristic polynomial is the determinant of 1 minus lambda, 0, 1, 1 minus lambda, which is just 1 minus lambda squared. So lambda equal to 1 has algebraic multiplicity equal to 2. However, the reduced row echelon form of A minus 1 times the identity is equal to 0, 0, 1, 0, right? Which if you translate to equations, just says y equal to 0. So the eigenspace corresponding to 1, right, the set of solutions, solve the xy, where y is equal to 0. So that's just x times 1, 0 with x arbitrary. And that has dimension 1. So in this case, lambda equal to 1 has geometric multiplicity equal to 1. So this eigenvalue and this matrix are deficient. Okay, so that's where the lecture stops. So feel free to stop listening. What follows will not be on the exam or the homeworks. But I'll talk about historical context. And since we've spent the last 3 lectures talking about algebra, I thought I'd tell you about one of the greatest algebraists, Emmy Noether, a German mathematician who was alive from 1882 to 1935. Noether was born in the small German town of Erlangen, near Nuremberg. Her father was Max Noether. Max Noether was a professor of mathematics at the University of Erlangen. But Emmy Noether was forbidden from attending classes there on account of her gender. Discrimination was a constant fact in her life. She attended classes both at Erlangen and then briefly at Göttingen, but she could only audit the classes. She wasn't allowed to sign up. And she had to go ask each professor individually for permission to sit in on their class. In 1904, the rules changed and she was able to register for classes. She got her PhD in 1907 in Erlangen, working with algebraist named Paul Gordon on something called invariant theory, which roughly speaking studies algebraic symmetries. Noether worked at the Math Institute of Erlangen without any pay or a title from 1908 to 1915. During which time she shifted from the very concrete approach to algebra of her advisor, Gordon, towards the more abstract approach that had been initiated by David Hilbert. Gordon himself did not like what Hilbert had done. He had complained about one of Hilbert's early papers that that's not mathematics, that's theology, because it was all very abstract. This was an existence theorem that wasn't constructive. But this abstract approach of Hilbert, Emmy Noether became an expert on it, and she became renowned for her applications of this method. In 1915, she was invited to go to Göttingen to work with Hilbert and with Felix Klein on Einstein's theory of general relativity, which had been published just that year. Notice this is in the middle of World War I, so not a brilliant time to be in Europe. especially, well, Germany didn't have it as bad as France, but not a great time to be there. Noether was not allowed to hold classes in her own name. Instead, her classes would be announced as classes to be taught by Hilbert with the assistance of Noether, although Noether would be doing all of the teaching. This was a way that Noether and Hilbert had come up with for Noether to be able to teach classes, getting around the restrictions about women teaching classes. Once World War I ended in November 11th, 1918, there was a revolution in Germany, and this revolution brought about more rights for women. In particular, Noether was able to complete her habilitation, which allowed her to lecture in 1919, although she still taught without a salary, which she finally began to receive in 1922. Her status at Göttingen was held back not just because she was a woman, but also because she was a Jew, a social democrat, and a pacifist. During the 1920s, Noether did foundational work on abstract algebra, working in group theory, ring theory, group representation, and number theory. Her conceptual approach led to principles that unified disparate theories and marked her as an extraordinary mathematician. She received international recognition and awards. Nevertheless, in 1933, when the Nazis came into power, she was denied permission to teach. It became too dangerous for her to stay in Germany, so she accepted a guest position at Bryn Mawr College in Pennsylvania. She also lectured at the Institute for Advanced Study in Princeton, which is where Einstein had ended up for similar reasons. Noether died suddenly in April 1935 while recovering from an operation in which a tumor had been removed. She was only 53 years old. Noether's results are often too abstract to state without a lot of preparation, but I'll mention a couple that can be stated simply. First, she transformed topology with a simple idea that she didn't even publish herself, but instead she generously shared with some young topologists, and they published it. So suppose we're looking at a two-dimensional surface, such as a torus, right, or a donut. Or you could be looking at a donut with two holes, right, or however many holes you want in your donut. Before Noether, people computed the Betti numbers, named after an Italian mathematician. So you'd have B0, which would be the number of connected components. B1 would be equal to the number of one-dimensional holes, loosely speaking. And B2 would be equal to the number of two-dimensional holes. Again, loosely speaking. So for, say, the torus, the donut, you would have one connected component, right? So B0 would be one single two-dimensional hole, the interior of your donut, and you'd have two one-dimensional holes. So you'd have one over here, and you'd have another over here. Right? So in this case, we have 1, 2, and 1. So before Noether, people just were working with these numbers. Whereas Noether came up with the idea that instead of keeping track of just these numbers, you should keep track of the vector space of chains. So instead of looking at B0, you should look at H0, H1, H2. And these are now vector spaces. Well, they're vector spaces when you're working with real coefficients anyway. And Noether's idea was that if you keep track of these, then every time you have a map between spaces, you end up with a map, a linear algebraic map between the corresponding vector spaces. So you go from geometric maps to linear algebra maps, right? This allowed transforming problems from geometry to algebra and revolutionized topology. Anytime you can connect two different areas of math, that's extremely powerful. And so now we have a whole part of math called algebraic topology, which just keeps going with Noether's idea. So I really like that contribution she made. Another contribution, which is more famous, especially if you're not a mathematician, is a result in physics called Noether's theorem. So this is something that she came up with once she got to Göttingen. So Hilbert and Klein invited her to Göttingen to help them understand relativity, because Hilbert was very worried about conservation laws in general relativity. And so Noether came up with this marvelous theorem that not only explained what was going on in relativity, but explains what's going on in every physical theory. This theorem says that every symmetry of a physical system is connected to a mathematical conservation law. So for example, if you have a physical system that is symmetric with respect to translation, so just moving left and right or front and back, then you have to have conservation of linear momentum. If you have a physical system that is symmetric with respect to rotations, then you have to have a conservation law for angular momentum. If you have a symmetry that tells you that moving time forwards and backwards doesn't change the physical laws, then that system has to have conservation of energy. Notice the symmetry refers not to the particular object you're studying, but the symmetry of the physical laws that are governing the system. Noether's theorem has become a fundamental tool in modern theoretical physics. There's this book written by a couple of physicists called Symmetry and the Beautiful Universe, where they say that Noether's theorem is certainly one of the most important mathematical theorems ever proved in guiding the development of modern physics, possibly on par with the Pythagorean theorem. Right? That's how important this theorem is. Okay, and we'll stop there. Pick it up next time.